Hello and welcome to our talk. My name is Daniel and I will start with introducing you to Rowhammer. And you might remember Rowhammer JS. It took the known Rowhammer attack and was able to gain root privileges just from a web browser, from a website. How do we get to these bit flips? Well, Rowhammer is a problem in DRAM cells. And if you look at DRAM, you will see that this chip is split into multiple banks and you will have rows, maybe something like 32,000 rows. And these rows also have a row buffer. If you read from a row, then things have to be copied into this row buffer. The rows themselves, they store the single bits, and that's basically capacitor and a transistor. The capacitor is charged to store a value of 1 or 0. Okay, and the next step, how does Rowhammer work? Well, these cells, these are capacitors. They leak over time, so they need to be refreshed regularly. And what you can do here is you can access certain rows in this DRAM bank, and by accessing a row, you will discharge not only the cells that you are reading and copying into the row buffer, but also close by cells that are in proximity to these cells. And this is what we call the Rowhammer effect. So to guarantee data integrity, you have to refresh very frequently so that this effect and other effects don't occur. So you activate a row, you copy it into the row buffer, you activate the other row, you copy it into the row buffer, and then after some time you see bit flips in the middle row. Now, what can you do with that? Well, you can exploit this in different ways. For instance, flipping bits in code. And here's an example. For instance, if you look at sudo, there is this jump equal instruction that is used for the password check. If you enter the password correctly, then the jump equal will be true and it will jump to the location and will give you these elevated privileges. However, if not, then it will terminate and you won't get the privileges. But what happens if we flip a bit in exactly this jump instruction? Well, if we flip the first bit, it becomes the halt instruction, XOR, push, some prefix for other instructions, other jump instructions that might be exploitable already. And the last one, great. If we flip one bit, we go from jump equal to jump not equal. And then sudo will give anyone root privileges who does not enter the correct password, but not to the person entering the correct password. This is great, and this allows us to exploit Rowhammer. But DDR3 is affected, DDR4 is affected. Even ECC RAM can have errors that are not corrected by the integrated error correction. The question then is, if you think about SGX, Intel's SGX security enclaves, they are integrity protected. And this would prevent Rowhammer in principle because you would detect the integrity error.
Actually, Daniel, this is meant to be a talk about how to flip bits without Rowhammer.
Sorry, yes, I was getting to that, Kit. I was getting there, but can you please not just walk into my slides?
Well, I'll take over, shall I, for a little bit. So, let's talk about Plundervolt. Plundervolt is flipping bits from software, but without Rowhammer. And the first thing we did is we did something called fault injection.
Yes, I know what fault injection is. I do that all the time. So you have to have some specialized lab equipment, and you maybe need to solder some cables to the pins of the chip. And then you can play around maybe with the voltage or so to flip some bits in the chip.
You mean like the picture? Well, actually, not anymore. So now you can modify hardware from software. So you can effectively create hardware fault injection attacks using software.
Okay, so you say basically this replaces my whole lab equipment and so on with this memory mapped register? So what is that?
That's exactly right. So you can, in software, write to a memory mapped register, which then modifies the hardware. And the reason you might want to do this is because you might have a gaming machine that you want to respond really, really quickly, or you might have a computer in the cloud that you want to have low power consumption, or your machine might be getting really, really hot. And this gives the operating system a way to dynamically change maybe the frequency or voltage to protect the chip.
Okay, it sounds like a lot less hassle than like fiddling around with the hardware and all the time we short something and destroy something.
Yeah, and this is called dynamic voltage and frequency scaling. This has been used in the first of its kind attack in something called clock screw. Clock screw exposing the perils of security oblivious energy management. And what they did is in software, they modified the code which changed the frequency which caused faults. And from this, they were also able to fault something inside trust zone because the frequency and the voltage regulators are the same. They manage the same voltage and frequency, whether you're running untrusted code or theoretically trusted code. And this is their attack. They were able to infer a secret AES key that was stored within trust zone, and they were able to trick trust zone into loading a self-signed application. Not long after, there was another attack very similar called Vault Jockey. Again, this focused on an ARM chip, though. They were both attacks against ARM.
Wait a second. You're talking all about attacks that already exist. And yes, okay, we know you can attack ARM chips like that. But you know that Intel has a very, very big market share on desktop computers. So maybe we should also look at Intel processors. Yeah, but can you actually, can you do that? Can you underclock and overclock on Intel? I don't know. I actually did that when I was a teenager because my system was running too hot and then I undervolted it. And these tools, I also later on used this when I had some laptop. The undervolting made a huge difference. If you run a benchmark, you would undervolt the CPU, not change the CPU frequency. You would undervolt it, and then you would get a higher benchmark score because the CPU runs into throttling less often. And this is really interesting. That means you can actually change the voltage from software. And I've also used different tools here. For instance, I used the RM clock tool, but there are many different tools that you can use for that. And today it's quite normal that you would optimize the clock frequency and the voltage on gaming computers or also on laptops so that they don't overheat all the time. So if you look at these tools, you will figure out that they use some secret MSR, hex 150. And we looked a bit at this MSR and we can identify what bit serves which purpose.
Yeah, and this model-specific register, this MSR, has many functions, but we're just showing the voltage functions here. So you've got the offset, which is over and undervolting, and you've got static voltage. And we're specifically looking at undervolting. So let's have a look at C code and see how you actually run that.
So the first thing we're going to need to do is to set the frequency to be one specific thing because we're going to be modifying the voltage. So you want the frequency to stay the same but the voltage to be changed. And we're setting, for this particular machine, we're setting it to 1 gigahertz. And I'm just going to check that that has taken. And yep, we're now running at 1 gigahertz. And the next thing that we're going to need to do is to load the MSR driver because it's not explicitly loaded. And now we're going to look at how you actually change the voltage. So what you need to do is to open the MSR. See if you can spot the line of code that does that. Yep, there it is. And here's where we write to the MSR. And you only need to write to one of the CPUs because they all share the same voltage. You'll notice that we're writing to 2 planes, plane 0 and plane 2. That's the CPU core and also the cache. And you need to write to both of them because the MSR will take the higher of the 2.
And now that we know that we are able to undervolt, what can we do with that? Well, let's write some code to see if we can possibly get this to fault. Can you see what my code is doing?
Okay, let me check. So this is a while loop, and you initialized var and correct to the same value. And then you also compute all the time the same value again.
Yeah.
So this will never stop. Where did you learn to program?
Where did I learn to program? Birmingham University. So let's take a look at it in action. So here we go. I'm multiplying dead beef by 1122334455. I'm undervolting, minus 252 millivolts, 3, 4, 5. Oh, come on. Yeah, we got a fault. We got an incorrect multiplication result. And if you look at the XOR, it's a bit flip. So then we started just trying random numbers. So we're just generating a whole set of random numbers to see if we get any other faults. Can we fault a different multiplication? And again, we got another bit flip. So at this point, we just did lots and lots of random numbers. And we started to see not just one bit flip, but there you go. We've got more. We've got more bit flips and in different locations. So we have just managed to create bit flips by lowering the voltage in user space.
And this is where we come to Intel SGX, because we need root privileges to write the MSRs. So a user space fault in itself is not very useful, because if we're root, we can do anyway anything in user space, right? So that's where Intel SGX comes in. As Daniel said, it's a technology to create trusted areas, enclaves in your Intel CPU. So from an untrusted program, you can create an enclave and then call trusted functions in that enclave, but you cannot actually look at the memory of the enclave. So if, for instance, a cryptographic signature is running inside the enclave, you can kind of invoke signature, but you cannot actually extract the key.
But if you're the operating system, can't you just look at the data anyway?
No, so that's a crucial part of SGX. So even the operating system is untrusted, and the operating system cannot read the enclave memory.
So how is it protected then? How can you do that?
So that uses something called the memory encryption engine that encrypts and integrity protects all the data that is written to external DRAM. So whenever an enclave writes something to memory, it goes through this memory encryption engine, is encrypted with a key that is not accessible even to the operating system, and is then written into DRAM, and vice versa. When you read it back, the memory encryption engine will first check that the data has not been changed. For instance, not that you have not flipped a bit with Rowhammer or so in DRAM. And then only if that's valid, it will pass it on to the enclave and provide the decrypted data to the enclave.
Clever.
So if you inject a bit flip in enclave memory, say with Rowhammer, what you get is that you will basically crash the system. So you lock the memory controller and the system halts. So that's kind of like a denial of service attack, but you cannot do much more with that. So you cannot, let's say, flip bits inside enclave memory with Rowhammer.
You're saying that Rowhammer didn't work. So my question is, will Plundervolt work?
So yes, we will see that in a bit, and Plundervolt works because you inject the fault actually inside the CPU before the data is written into the encryption engine, and from there then to memory. So you kind of inject the bit flip in the CPU, and then it's encrypted, integrity protected, and written to memory. So here we can see your multiplication example inside an enclave. We go down in voltage 1 millivolt at a time, and then at minus 265 millivolts here, we have actually managed to flip a bit in a multiplication. And as you can see, that's actually exactly the same bit that we flipped in user space code before, but this time inside an SGX enclave.
So yeah, great. You flipped a bit inside SGX and it didn't lock up. You didn't get an integrity error, but it's just multiplications. What on earth can you use that for?
Well, the multiplication maybe not directly, but we can, of course, look at crypto. So I like to break cryptographic algorithms, and I used to do that with hardware fault attacks, and now I can do it from software in SGX. So, for instance, RSA, a well-known public key crypto algorithm, and very often when RSA is actually implemented, that uses optimization called the Chinese remainder theorem. And for that, we have a very, very effective fault attack if we can inject a fault into that computation. So I will not go into the mathematical details too much here. Just say that in normal RSA, you have a public modulus, which is a product of two prime numbers. And for instance, when you decrypt a message using your private key, you take the ciphertext to the power of your private exponent modulo n, and then you get the message back. Now in this Chinese remainder theorem, that is a bit more complicated. So kind of what you do is you split up the computation into two parts, modulo p and modulo q. And again, I will not go into the mathematical details, but if you manage to only fault one of these two sub-exponentiations, there are very, very efficient ways to recover one of the prime factors, and then you can just divide the public modulus n by one of the prime factors, and you get the other one out.
I've got a question. What are we're trying to get p and q. So what does that give us if we've got p or q?
So that gives you the private key. So you get p, and then you take the public value n divided by p, for instance, you get q, and then you can also compute this d, this private exponent.
So will Plundervolt be able to do that?
Of course, Plundervolt can do that. So there, just before I show the actual demo, there are two ways to kind of recover one of the prime factors from a faulty, in this case, decryption. So one is called the Bulck attack that needs the decryption once valid and once faulty of the same ciphertext. And the other optimized variant is called the Lanstra attack, and that can work with a single faulty decryption, which is great if there's some randomization in the scheme.
So we only need to get one fault to be able to get the private key out.
Correct. So let's look at an example. We have here an SGX function. So what we do in there is just use the Intel library function, IPPS RSA decrypt, which uses this Chinese remainder theorem optimization, and we undervolt until we get like a faulty decryption. So that we can see in this video here, we do an RSA decryption and actually first get a correct result, even though we're undervolting. So we try again get a correct result. Let's do another try, and again we will get a correct result this time. Now if we try a fourth time, finally we'll get our desired faulty results. We get a faulty decryption, and that we can now put into our little Python script here, which implements a Lanstra attack to recover one of the prime factors, in this case the value starting with EECF. And now to prove that we actually haven't cheated, let's look into the enclave code here, and let's see which kind of value was hard-coded there. And we'll also check like for the first few digits of our coefficient. And then we see that we have recovered P here.
So you've got the private key out of something happening inside an enclave just by undervolting.
Yes, exactly. And that is a thing that should not be possible, right? That's why there's integrity protection on the memory.
So if you can do it for RSA, what else could you do it for? Are there other more commonly used cryptographic algorithms you could try?
So yes, certainly. I like to break crypto, so I'll stay a bit more with the crypto. So yeah, the question is, what else can we break? And now we look at AES, which is probably the most popular symmetric encryption algorithm. It's all over the code base of SGX, even in the SDK of Intel for various operations. Internally, it uses a 4x4 byte state and applies 10 rounds of transformations on that. And
I was just thinking, maybe you could attack the brand new instruction set, Intel's brand new AES new instruction set, because that's really heavily optimized, isn't this right, to prevent side channel attacks?
Yes, correct. So in halfway new Intel processors, you have this AES and I instructions that allow you to do AES very quickly and also protect against some side channel attacks, but this only protects against timing attacks. So it will not protect you against a fault attack. And luckily, there's again also a very efficient fault attack on AES. So that works like this. You inject a single byte fault into the 8th round of AES, into the state, and then that will propagate, and through some mathematical operations, you can recover the complete AES key from only one correct and one faulty encryption or decryption of the same input. So here we have the implementation of that inside SGX. So we do, as you see here, twice the same operation. So normally this loop should never terminate because the result is always...
Can I ask, why are you now doing the same operation twice?
Because we need one correct and one faulty encryption in this case. By the way, this is of course just pseudocode, so we're not really comparing this pointers here, just for like people who wondered. So there's an actual memcompare happening there. Okay, so let's see that in action in SGX. So we call AES encryption here with minus 262 millivolts, and we got a fault here in the 4th round. That's actually too early, so we do it again. Here we have a fault again in the 5th round, so too early. So we'll run the attack again, another 5th round. And then finally in another attempt, we'll get the desired location, which is the 8th round. And now we can use the faulty and the correct ciphertext and put that into our differential fault attack. And as you see here, we actually use 2 pairs on which we run the differential fault attack. This is simply because the attack will give us multiple key candidates, and then we can use the intersection of the 2 results to find the correct keys. So here you see the attack running. We recovered the keys for pair 1 and pair 2, and we take the intersection and recover the, in this case here, the correct key, which is 00, 01, 02, and so on. So just to show that we didn't cheat, let's look at the enclave code, and let's grab for the key, and indeed we recover this value. So as I said, we used 2 pairs in this example. You could also get away with 1 pair and then brute force over all the candidate if you have a known plaintext, for instance.
Brilliant. So now we've got keys out of both RSA and AES new instruction set. But that's just crypto, and I don't really get crypto. Is there anything else we can do with that?
Yes, I think we could do something with that would relate more to system security. I would say it's not just crypto. For instance, if you take a simple code snippet like this, we take a pointer to some array offset, and then we want to store something there, an enclave secret, maybe a secret key or something.
But Daniel, what's that got to do? There's no multiplications in there. That's just pointer arithmetic.
That's right. But pointer arithmetic implicitly uses multiplications. So if you would rewrite this array access there, then you would get this code basically. Just foo equals array plus offset times the size of the structure that you were addressing here. This is simple pointer arithmetics. I think that many people will know that from their C programming classes. And of course, then you have a multiplication, so that's something that we can fault. So maybe we should try that. If we fault this multiplication, we will get to the wrong offset, and then hopefully we will write to a wrong location and see what we can do with that. Okay, so in this example, we have an enclave with a base and a limit. So within this region, this is secure memory that the attacker cannot read. So staying between here and here is secure. Now, if we run this many times, we will see that at some point we have a fault, and this fault means that we started writing to this same location over and over again, and now we had a fault, and it now writes to a different location outside of this secure region. And that means that we can read what the enclave wrote there, and we can see that it wrote dead beef there, which is in this case the secret that we have implemented in our enclave. Now this is pretty bad. So if we go back to the graphic, you can see that clearly only writing within this green area, this is secure. Writing to the faulted location outside to user memory means that the user directly can read this value. Well, the question then is, of course, if we can induce faults like that, how difficult is it to produce these faults without running into a lot of trouble?
Yeah, I get asked this question. I have to say, this is probably the question that I have been asked more than any other single thing. So let's talk about that for a bit. The first thing that we did is, for all the computers that we were able to fault, the first thing that we did is we ran a benchmark. We found out what was the voltage when it was idle and at what point did it crash. And what we wanted to know was, how close to the crash point do we need to be? And I have to tell you, I had some spectacular crashes. When this is my favourite crash. They weren't all as colourful as that, unfortunately. But here you can see, this is an actual graph of a crash and a fault. And it looks like they're pretty close together. But actually, if you get to the frequencies in the middle, we found those to be the most stable. And you've got maybe sort of 20, maybe 10 millivolts to play with there. So you've got just enough to keep the computer stable. But we also found out some other things. We found out that if you try and buy two identical, I only mean absolutely identical computers, and then you benchmark them, they might look different. And that was one of, yeah, that's weird.
So that means that although I bought exactly the same machine, I will get basically more performance out of, or I might get more performance out of one because it produces less heat.
Yes.
Interesting. I didn't know that.
Yeah, we actually thought we were buying exactly identical machines, and we weren't. But this is why the benchmarking portion is really important before you start faulting. We also found out that we were able to make a machine more stable by maxing out the cores, because you needed more undervolting when they were idle, and consequently I was getting more crashes. But if we maxed out the cores, then you needed less undervolting. And let's have a quick look at an example of that.
Firstly, I'm going to run the multiplication while the cores aren't under a huge load. And we get our first fault at minus 163 millivolts. Incidentally, these are all things that we haven't demonstrated before. None of this made it into the paper. So let's max out the cores now. And now we get a fault at minus 153 millivolts. That gives us, 10 millivolts to play with to keep our system stable.
But there's some more things. I thought this might be kind of fun. Let's just see what else I can fault. So first of all, I'm going to have a go of faulting cat. I'm just going to cat a program and I'm going to undervolt. And you can see the text being written to the screen. And there we are. We got a core dump with cat. Let's try something else. How about trying find? I'm just going to find a file I know is on my computer and I'm going to undervolt. It found it there and then it core dumped again. So we can force find to core dump. How about ls? I piped it to a file, otherwise my screen filled up with rubbish. And ls, yes, we even managed to get a core dump with ls. That's minus 181 millivolts, so that was quite hard. How about verifying a signature with OpenSSL? Yep. Again, we got a verification failure at minus 167 millivolts. And that was kind of a bit of fun just to see there was an awful lot of things we were able to fault.
Okay, so Kit, hang on a second. So you said that you can kind of crash some programs. Sounds to me like denial of service, or do you think there's some more to it?
I think by undervolting, we're managing to get the program to do something it shouldn't. And that's kind of interesting because this could be something that you could attack possibly in the future.
So we reported this to Intel, and Intel confirmed that we were the first reporters. They also issued an embargo, and we complied with the embargo. And during this embargo, there were also other reporters who also discovered the same vulnerability. For instance, the Vault Pawn team and the Vault Jockey team, they also discovered that you can induce faults by playing around with DVFS on Intel processors. They also participated in the embargo, and all of this then went online at the same time.
So in summary, we created a new type of attack against Intel SGX. We broke the integrity of SGX, and within SGX, we were able to retrieve AES new instruction set keys. We were able to retrieve an RSA key. We were able to induce memory corruption in bug-free code. And we made the enclave write secrets to untrusted memory. Not only that, we were able to get some Linux binaries to core dump. And a massive thank you to the grants that make this research possible. And a massive thanks to you for watching this talk and for hopefully making it all the way to the end. Thank you. And I look like a bit of an idiot.
Okay, we're live.
No, we're not. I don't think not on.
I think we're live now. Okay. So we got a few questions in the chat, and just keep posting the questions. So one of the last questions that we got was...
Wait, we're not live.
I do think are we? Yes, we are live. So one of the last questions that we had was whether the susceptibility to bit flips comes from differences in the chip manufacturing. And we can only say we don't know, basically. We just observe that they are susceptible to Plundervolt bit flips.
Yeah.
And that's it. And we've seen differences. Same processor, right? You had one example, the same processor, and it was susceptible to bit flips at a different voltage level.
Yeah, and we don't think I'm 100% live. Thanks. We don't think it was differences in production line, because I think they would be tiny differences. But I do think possibly the way it's set up or something like that, the way the differences in the way the chips are prepared on the motherboard as they go out, which would be kind of interesting to know. I would love to go and have a peek at the way Intel do things and ask them, but I don't think they're going to let us know.
So a lot of good feedback. Thank you for the positive feedback.
Yeah, we did actually, we filmed it. If you're interested, we tried to film it live across three different places. So we had 2 different countries and 3 different locations, and we actually did it as live whilst recording ourselves. So thank you very much, because it took us a long time to do that. So thanks for the appreciation.
So there's
Xeon.
A question: are there similar capabilities to MSR on other architectures? Well, there is on ARM, right? There were already papers on that. The Volt Jockey paper, for instance, that did some manipulation of voltage frequency scaling on ARM. So yes, there are.
I think someone said, does this apply to Intel Xeon chips as well? Because you've got a Xeon machine, haven't you?
Oh yeah, we have Xeon machines. I would expect that it's applicable just the same. Yeah, I don't see a difference there.
Is there any way to protect against this attack? Well, unfortunately, the way to protect against it is to turn the MSR off, which is what Intel have done. But you have a choice. You can either have SGX or you can undervolt. And I have seen a lot of people talking about newer machines that appear to be coming out without the ability to undervolt, which is a shame, I think.
It's an interesting situation, because for more constrained devices, it was always possible to implement protected algorithm. But in this case, it's unclear what you attack, right? If you don't attack the crypto, then you attack something else like pointer arithmetic. And suddenly it's much more difficult to protect against that in a generic way, more difficult than for certain crypto algorithms.
Thank you, Marina. Thank you.
How did you become interested in lower level fault attacks as individuals and a team rather than applications?
So the fault attacks, I mean, let's be honest, we can openly say that Clockscrew was the first of its kind. And Clockscrew is an absolutely fantastic paper, and it opened the world to new attacks. And
it's because of clock screw that we've gone on to see a number of attacks against lots of other chips. So that was where we started. But as a team, I think this is what you're asking. As a team, we came together because we all brought different things to the table. And so at Birmingham, we didn't have as much experience as Daniel's got for fault injection. And so when you come together, each brings something that adds to the overall research.
Mm-hmm. I think the interest for topics like this from my side came actually from my PhD supervisor, who said, well, this is an interesting area. Take a look at that. Okay, thank you. A lot of
do you plan to continue this research? Yeah, we at Birmingham have been looking at AMD. I don't think we've had much success. I'm not working on that specifically. Yes, the code is available. It's on GitHub. It's /Kit Murdock, which is my name, or Kit-Murdock. It's either Kit Murdock or Kit-Murdock. Try one of the two. And that's where we've got the code to modify the MSR and also to create a fault in one of the cryptos. It might be both of them. Can't remember. That's not very helpful.
Why do identical products produce different results? A bit unclear there. We had in the team, we had multiple small NUCs with the same processor, with the same, basically the same processor, same microarchitecture, same specifier what the processor is, but different voltage baselines. So apparently, even the same processor, as you buy it with exactly the same number, can be different, and that has a lot of consequences. For instance, also, and I find that a bit concerning, that these might even lead to performance differences in benchmarks if one has a higher performance level than the other, higher voltage level than the other.
Someone's asked, how much time roughly does the attack take to carry out? Well, it can be seconds. The hardest bit is the benchmarking, which takes hours because you're crashing your computer, just constantly crashing it. But once you know where the crash point is, you just stay a little bit above that. And at that point, you can, seconds, seconds.
What vintage is that? On my side, some Austrian local wine.
This is awful because it's written in English and we don't produce red wine in England, so you know that it is not a good bottle of red wine. Bear in mind that we're in Europe, so we're allowed to drink. Because it's evening. I think that's all the questions. There's a question. Could the MSR be protected admin access required, for example? So the MSR does require admin access, which is root. You have to be root, which is why the application of SGX is where we focused all our attacks, because SGX says you should be protected even against an attacker who has root. And you're not, because of Plundervolt.
In general, you can fault any application, but as Kit just said, you need root privileges to modify the MSR. If there are other ways to induce faults without that, or if someone would introduce an interface where you don't need root privileges to induce faults, well, then you could also very realistically attack other applications.
Someone is schooling me on red wine production in the UK. We do produce red wine. I apologize. Another question. Are there similar capabilities to MSR on other architectures? Yes.
Yeah. Clock screw on
Clock
ARM.
screw is on ARM, yeah. And AMD, who knows? There's an area of research for you.
How reliably can you get the fault into the 8th operation of AES?
So it was pretty evenly spread.
Yeah.
So 1 in as many rounds as there are. 1 in 11. I am not a cryptographer.
Well, yeah. At this point, let's thank the audience. Thanks for being here. Thanks for all the very positive feedback. And if you have any further questions, just send us a mail or ask them through some other means. We are always happy to answer questions.